Let's get some practice with indexing vectors using our sensitivity analysis of exponential decay based on first-order kinetics. I'm going to go ahead and run this code again to make sure our global environment is populated with all the variables created by this code. And recall that we're calculating concentrations that are corresponding to several different times during the experiment. So if we look at the concentration vector, we have values starting at the initial concentration 50, following an exponential decay curve until we get to the end of the experiment at about 60 minutes. Now let's say for this particular sensitivity analysis, we're only interested in the first 99% of the consumption of the original reactant, meaning that we only care about the concentrations that are greater than 1% of the initial concentration remaining. So how do we do that? Well, we use logical operators in R. Logical operators work a lot like mathematical operators. It's just that they return logical values based on comparisons rather than numerical values. So one operator is the less than operator. I'm interested in all of the concentrations that are less than a given value, and in this case, that's 1% of the initial concentration. Now remember that these are two different lengths of vectors. 0.1 times const init, well, that's just a single value. That's a vector with just one element. Const is a vector with 121 elements. So R is going to do the same thing that it does with arithmetic operators, and that is going to recycle this one value as many times that it needs to do this operation on this whole vector. That means when I run this, I'm going to have 118, 19, 20, 21. So that's exactly the same length as the original concentration vector. But I have one logical value in each of these that is the result of this comparison. Now this is exponential decay, so it makes sense that there are going to be a whole bunch of falses that are all values that are above 1% of our const in it. And then we're going to get at element number 92, 3, 4 to the first element in the decay that's less than 1% remaining. And our exponential decay is monotonic. It's only going down. It's not going up. So it should make sense when we look at this that all of these values are true. We would be really confused and perhaps looking for a bug if that wasn't the case. So all of the remaining values in this exponential decay are less than 1% after the first one that's less than 1% at element number 94. So this vector of logicals is by definition going to be the same length as the original concentrations. That means we can use it as an index to index that original concentration. So let's say what we want to do here is make a copy of concentrations that we're ultimately going to filter. So I'm going to call this concentrations filtered. I'm going to assign that to the original concentrations. Then I'm going to set the values using the index based on this comparison of this new vector, and I'm going to set it to NA. Now this gives us a good excuse to talk about NAs in R. NA stands for not available, and it's a special value for every data type that simply tells you that the data are not there. Now you might be tempted to put like a 0 in here, but that would be a really big mistake, because especially when you're doing statistics, 0 is a meaningful number. It's data. It doesn't mean you don't have the data. It means that you took a measurement and you got the value 0. So we don't want to use a 0 here. We want to say we're filtering this data out. These are data that we don't want to consider through the rest of our analysis. So in this case, we are going to be assigning an NA value to all of the elements of the const filtered vector that represent values that are less than the initial concentration from the original vector. So let's go ahead and run this. Now, our concentration vector hasn't changed. We made a copy of it, so we haven't altered it, but we have created a new vector of filtered concentrations where every value that is less than 1% of the initial concentration is now an NA value. So we've got a filtered version of our data that for this particular sensitivity analysis, we care about what time that 99% of consumption happens, and we only want to think about the curve up until that time. Of course, I should add a comment here, and we can say that we want to filter the data to only consider the 99% removal of the original reactant concentration.